All right, we are into chapter 13. This is the shortest of our 5 chapters that we cover this year, but it does have a lot of material in it, even though it is a short chapter. This specific section, not too long. Should be pretty quick and easy for us. All right, so 13.1, we are talking about vector functions and space curves. So vector functions, meaning an actual function of vectors, and then space curves, which is kind of what they create. All right, so let's go ahead and we'll just kind of jump right into it. We're going to be able to define algebraically and graphically what a vector valued function and space curve is. So here we've got our three-dimensional plane, and maybe we've got a curve that does, I don't know, I'm going to put this thing all over the place. So maybe it comes over here, and then it drops below the x-axis, so I'll dot that. And then, maybe it comes back up this way, and it wraps around the back of the z-axis, so I'll dot that. And then it slides around here, and then it goes underneath the x-axis again, behind the original curve. Just it can go anywhere. It's all over the place. So that is some kind of a space curve. A couple of things about the space curve. One, the direction does matter. So when you're drawing one of these things, it's actually going to be important that you kind of label the direction that this thing goes in with these little arrows, which kind of tells you, again, the direction that this space curve is going in, because the direction does matter. And then, maybe you're going to have some kind of a point right here, and that specific point on the space curve is associated with, maybe that's what t equals 1. And then maybe you've got another point, maybe out here where t equals 2. And then obviously all the points in between are between t equals 1 and 2. And then if you go backwards, t would be, negative values and stuff. It's fine to have negative time values. And here we're just talking about time before 0 or whatever t is valued to be. So how do we actually define a space curve? Well, in general, it's going to be parametrically defined. So x would simply be some function of t. Y is going to be some other function of t. And z would be a third function of t, where t is the parameter. So we're kind of going back to parametric type stuff here. So t is the parameter. But why is it actually called a vector valued function? So what does that actually mean? It's pretty simple, actually. In order to get to t1, in order to get to t equals 2, you have to have a vector which comes from the origin, which hits that specific point. Let me kind of illustrate that down here a little bit for you. So again, maybe we've got some kind of a curve on the XYZ, that one looks horrible, on the XYZ axis. And again, who knows, maybe it does something like this and then wraps around underneath. It comes out here. I'm just going to draw this one a little simpler. So what you've got is, in order to get to this point right here, there's a vector that comes from the origin out to that specific point. Whatever that vector is, that's associated with maybe t equals 1. And then I've got another vector which comes from the origin. Whoops, did not mean to erase. Which comes from the origin out to this point, and maybe that point right there is t equals 2. And what you have is you have an infinite number of vectors coming from the origin that create this curve. So there's another vector, there's another vector here, there's another vector here, there's another vector there, there's another vector there, and technically there's an infinite number of vectors that are going to point out to every single point on this curve. So the vectors will actually create the curve. There's an infinite number of vectors that create this curve. So that's why it's called a vector valued function. And why is it a function specifically? So the idea is that no one vector that comes from the origin can hit two different points on a space curve. Okay, I can't take the vector, like, I don't know. So let's just say, for example, that our r of t, which is our space curve, is defined to be, f of t, g of t, h of t, like we did above. And then maybe r of 1, which would be associated with time 1, is, I don't know, 3, 5, 2. I'm just making that up completely off the top of my head. 3, 5, 2. That's probably not what that point is, actually. So this is just made up. That's not what the actual point is. But anyway, so vector 3, 5, 2 gets us to the point where t equals 1. And then, whatever you get when you plug in 2 into your r of t, whatever you get when you plug in 3 into your r of t, and so on and so forth. All of those things are going to create that space curve, that blue curve. Every single possible value for t that we can plug in will create that space curve based upon where the ends of the vectors are going to be. All right. A little bit longer even than I wanted to spend on that part, but I think it's important that you guys understand what a vector valued function and why it's actually called a function, because again, 3, 5, 2 can only point to one specific spot if it's coming from the origin. And in this case, we just said it would be there. That's really not 3, 5, 2, I'm sure, but that's what it is. All right. So the vector r of t, and that's typically what we use for the vector notation for a space curve, has the property that if emanating from the origin, that's what I said before, so it has to start at the origin, emanating, nice fancy word there, SAT word, the tip of r of t will trace out the space curve as t increases, or technically as t decreases, depends on which way you want to go. Also will depend upon your domain for t. From that perspective, we are going to have to talk about domain. We'll get to that in just a second. But let's actually go ahead and just kind of try and draw one. Let's try and draw or sketch out a space curve. So if r of t is defined to be t cubed I plus 1 over tj plus the square root of t plus 2k, and we want to trace this curve between t equals 1 and t equals 2. So let's go ahead and sketch an XYZ plane here. X, Y, Z. So it might be easier, and if you're like me, it's just easier to see if I actually write r of t in vector form with the brackets as opposed to ijk form. So that's going to be t cubed 1 over t and square root t plus 2. So if I want to kind of sketch this, it would help to know the starting and ending point. So r of 1, well, that's just plugging 1 in. So that's going to be 1, 1, root 3. And then I kind of need to know where the ending point is, r of 2. That's going to be, let's see, plugging in 2. 2 cubed is 8. 1 half. And then plugging in 2, we get root 4, which is 2. So that gives us kind of a way to sketch this or trace it out. So when r equals 1, I'm at the point 1, 1, root 3. So when r equals 1, I'm at the point 1, 1, root 3. So maybe that first point is right here. That'll be associated with t equals 1. And then if I'm going to be at t equals 2, I'm going to be at the point 8, 1 half, 2. So let's do this one in orange. 8, so that was 1, so 8 is someplace way out here. 8, a half, which is like half the distance there, and then 2. So it's going to be a little bit higher than root 3 was. And then this right here would be that second vector. And obviously, if you wanted to be make it extremely accurate, you would have to do all the points in between. But a lot of times we can kind of tell what this thing looks like. T cubed, 1 over t, square root of t plus 2, those are all continuous functions between 1 and 2. So there really shouldn't be any kind of weird thing going on here. So it looks like I'm just going to have some kind of a smooth curve that kind of bends up from the lower one to the upper one. And again, we're going to put little arrows on this thing just to indicate direction. So that's kind of what that space curve would look like between t equals 1, t equals 2. Okay, not a really fancy graph or anything like that, but that's it. I mean, that's the general idea. So in order to do this, again, we do have to know something about the domain. So how are we going to figure out the domain? What is the domain of this space curve? Not from t equals 1 to t equals 2, that was given to us, but of the actual space curve r of t. Well, what we have to do is we have to take the pieces of this and figure out each individual piece's domain and then put them all together. So the domain of the x piece, let's see, the domain of x, that's t cubed. That's all real numbers. So I don't have any issues with the domain of x. The domain of the y piece, 1 over t, well, we know that you can't have 0. So t simply cannot be 0 for that one. And then z, it's a root function. So square root of t plus 2, t is going to have to be greater than or equal to -2. If you don't remember how to do that, remember you just take what's underneath, t plus 2, make it greater than or equal to 0, and then solve. So you would get t is greater than or equal to -2. So we have to put all those pieces together. Well, x is anything, so that's not going to really be an issue. But we know t can't be 0, but t also has to be greater than or equal to -2. So our domain for overall for this function, our domain is going to be from -2 up to 0, because you can't include 0, and then in union with 0 to infinity. So there's your domain. So again, put all the pieces together, make sure that you're getting the intersection of all the pieces. It's not all of them, like it's not the union, it's all of it's the intersections. Okay, so we're going to talk about the domain, and then we're going to also throw the limit in here on this next one. So let's talk about the domain. Go piece by piece. So for x, well, that's 2t minus 1. It's linear. It's all real numbers. All polynomials are always all real numbers. Sine of t over t. Sine of t itself is not a problem for anything, but the dividing by t means that we can't have 0. So y, again, t cannot be 0. And then the z part. You got a natural log. Remember that you cannot take the natural log of 0 or a negative number. So whatever's inside the 1 plus t, whatever the argument of the natural log is, has to be greater than 0. So we know that if we take 1 plus t and set it greater than 0 and solve for t, you would get that t has to be greater than -1. So our overall domain of this function, of this vector valued function, let's see, t has to be greater than -1, no equal to, so it's got to be a parentheses, up to 0, and then from 0 to infinity. So there's your domain of that vector valued function. The limit, this is really nice, the limit of a vector valued function is literally taking the limit of each individual piece. And we are taking the limit as t approaches 0 in this case. So our limit as t approaches 0, if we actually were to write it out long way, and I won't do this every single time, but it'll be the limit as t approaches 0 of 2t minus 1, the limit as t approaches 0 of sine of t over t, and the limit as t approaches 0 of the negative natural log of 1 plus t. So then you can just take the limit of each piece. So we're going to have to go back and remember some things about limits. The first one is linear. Again, that's a direct substitution. I can plug 0 in. We're going to get the limit of that one to be -1. If you don't remember this one off the top of your head, if you plug 0 into sine of t and t, you're going to get a 0 on top, 0 on the bottom. Perfect time for L'Hopital's rule. Taking L'Hopital's rule, you would get cosine of t over 1. Then directly substitute 0 in for cosine of t, and you're going to get 1. And then the last one, if I were to directly substitute 0 in, you're going to get the negative natural log of 1. Natural log of 1 is 0. Negative 0 is still 0, so you get 0. And that's your limit as t approaches 0. All right, I think we're going to stop there. We're going to come back with one more short video, and this should not be a very long lesson overall.